Continuing on from the previous video, the last special scenario that we're going to look at is dealing with range. So range is basically the horizontal displacement Sx when Sy has returned to 0 meters. So in other words, the projectile has returned to the same height from which it was originally launched. Now the reason why this one's important is due to the symmetrical nature of projectile motion. So basically that idea of what goes up must come down. It means that we have a simplification we can use here in that the velocity going up is going to be equal to but opposite the velocity when it comes back down. So if we look at Sy when it's equal to 0, so the object's gone up and come back down again, then we have that Vy is going to be the same speed as the initial velocity but in the opposite direction. So we can say that Vy is equal to negative Uy. So that will make it a little bit easier to figure out or to substitute into the equations when we're looking at this idea of range. To put that into context, let's consider a scenario where we're dealing with, say, a golf ball that's sitting on a tee, and that golf ball is going to be struck by a club. Let's say it's a driver of some description. So as that driver is being swung, it's moving with some velocity. It's going to collide with the ball. It's going to cause the ball to then move off at some velocity. So we'll say that that velocity is 52 meters per second, and the angle that makes with the horizontal is 47 degrees. So the question here might be something like calculate the range of the golf ball. So if we consider the motion of the ball, it's going to travel up and then come back down again and strike somewhere on the ground, somewhere in the distance. Obviously this isn't to scale, otherwise that's a ridiculously large driver. But ultimately we're going to ignore this height of the tee. We'll just say it's close enough to the ground that that's negligible. So the distance that we're interested in then is this length here, which is Sx. And we know, as I said, that if we break up this vertical and horizontal component of the initial velocity, so we'd have that as being Uy and that as being Ux, we can do the same over here. You can see that there'd be some final velocity down this way, so that would be V, and we know that we can break that up into components as well. So that's going to be Vy. So we can say that that's equal to negative Uy, and that will be Vx. And we know that given that there's no acceleration horizontally, we know that Vx is going to be equal to Ux. So if we want to go through and solve this, the first thing we need to do, as we've been saying, is to define the direction that's going to be considered to be positive. Now because it's going up and coming back down, it's probably going to be easier to work with up being the positive direction so that our initial velocity is positive. So let's go that up is positive here. And so to go through and solve this particular question, we first need to resolve the initial velocity. Ux is going to be equal to U cos theta, and so that's 52 cos 47, which is equal to 35.46 meters per second, and Uy is going to be equal to U sine theta, so 52 sine 47 degrees, and that gives us a value of 38.03 meters per second. I'll just mention here as well, sorry, that again Ay is equal to the acceleration due to gravity, and because that's in the downwards direction, that's negative 9.8 meters per second squared here. Just to reiterate that point. So to find the time when sy again is equal to 0, we can use the equation Vy is equal to gt plus uy. That means that we can substitute in here and say that this value is going to be negative uy, so Vy being equal to negative uy, and that's then going to be equal to gt plus uy. So notice now that we've simplified things because we've got two terms of uy. If we collect those terms, we'd end up with negative 2uy is equal to gt. And so we can solve for t. So t is then going to be equal to negative 2uy over g. So that's negative 2 times 38.03 over negative 9.8. Again, see that the two negatives are going to cancel here, and so that gives us a time of 7.76 seconds. So we now know how long the golf ball is going to be in the air, so that means we can find the range. And that's just finding that horizontal displacement. So to find the range, Sx is going to be equal to Ux multiplied by t, and Ux was 35.46, multiplied by that time 7.76, and we get a value of 275.25, and then rounding to the correct number of significant figures, that would be 280 meters, so to two significant figures. So there's the range of the golf ball in that particular scenario. Now, just to generalize a little bit here, if we consider any other scenario, so basically anything that isn't a special scenario, it's just a matter of following the usual steps that you would for any projectile motion problem. So some of the things that you're going to need to do there is to resolve the initial velocity into components. So that would usually be one of the first steps, obviously after you've defined positive and negative in the vertical. You'd then go through and apply the equations of motion as needed, depending on the information that you've been given in the question. And basically then, after applying the equations of motion, the purpose of that is to calculate the unknown quantities. And that may involve combining components to find, say, the final velocity. So to give an example of that, let's have a look at one last scenario. And in this case, we'll have something along the lines of a ramp that's at an angle of 22 degrees to the horizontal. The ramp has a height of 2 meters. And off the top of that ramp, we're going to have some sort of stunt person riding say a push bike or a motorbike or something or other that, let's go a push bike. So that person's going to be pushing hard on those pedals to get the bike to move at a fairly fast speed, and the speed that they'll be travelling at, I need to make sure he's wearing a helmet. The speed that this person is going to be travelling, or the velocity that they're travelling at here, is 15 meters per second. So the question here might be something like calculate how far from the ramp he lands. So that's finding that value of Sx. And we can do that, as I said, first of all by resolving into components. So we've got this, the initial velocity, we can break into the two components, so ux and uy again. So again, just drawing that diagram to make it clear what it is that we're actually trying to calculate. Always a good idea to communicate your understanding as much as possible. And so we would have here that ux again is going to be equal to u cos theta, and if we substitute into that, we'd have 15 cos 22 degrees, and that gives us a velocity of 13.91 meters per second. As I mentioned back in the previous video, sometimes I do forget this step. We'll make up as being the positive direction to make sure that we are considering what's happening with positives and negatives and not getting confused. And so uy then is going to be u sine theta, and that's going to be 15 sine 22 degrees, and so that gives a value of 5.62 meters per second. Note that that's in the upwards direction, so that's going to be a positive. The acceleration in the vertical direction, in the y direction, is going to be the acceleration due to gravity, and because that's coming back down, that's going to be negative 9.8 meters per second squared. Now, in order to answer this question, we need to find the time of flight. Now, the idea of time of flight, it's basically just how long it is that the projectile's in the air, and that's basically from when it's being launched or propelled to when it then strikes the ground at some later point in time. So to find the time in the air in this case, we don't have any information about the final velocity. We do know that, as I said, we're trying to find whatever the horizontal displacement is across this way, but we also have the vertical displacement here now as well. So that we've got this value of 2, so we know that the vertical displacement sy is going to be negative 2, because it's going to be coming back down 2 meters lower than where the bike took off from the end of the ramp. So to find the time of flight in the air, we can use the equation sy is equal to half gt squared plus ut. And so if we substitute into that, we'd have that that's a value of negative 2.0. That's going to be equal to half times negative 9.8 t squared plus 5.62 t. Now you'll notice here that we've got two terms with t in it, so one with the t squared, the other with the t, so it makes it a little bit trickier to go through and solve this. To make it easier to see, we're going to move everything onto the left hand side, so we end up with 4.9 t squared minus 5.62 t minus 2.0 is equal to 0. Now hopefully you can recognize the form of that equation being a quadratic equation, and we've got it set to be equal to 0, so we now need to solve for t, and there's a few ways that you can do this under exam conditions. First way is to use a quadratic equation. So if you can remember that, you can apply that and figure out what the value for t would be. The second way would be to use equation solver on your graphics calculator. Third way would be to graph it on your graphics calculator and find the zeros. So that would give you a parabolic graph, and then you'd find where that intersects the x-axis. And when you do that, you'd find that there are actually two solutions for t. So one of those solutions is going to be negative 0.285 seconds, and the other is going to be the solution of 1.432 seconds. Now, if you look at those two, fairly obvious, I think, that time has to be positive. So whenever you're recording the time, you sort of start timing and it counts upwards. So the time that we're dealing with here must be positive. So if you do go through and find those two solutions and one of them is negative, you can basically ignore that one. And so we know then that the time is going to be equal to 1.432 seconds. And that then allows us to find the horizontal distance. So that's the last step then, to find the horizontal distance. Again, is just that equation of Sx is equal to ux times t, and we found earlier that ux was 13.91, multiplying that by 1.432, and that gives us a value of 19.92. If we go back and look at the values that were given in the original scenario, they were all to 2 significant figures, so we should round that to 20 metres, and again, to express that 0 is a significant digit, we should really write that as 2.0 by 10 to the 1 metres. Now, if the question was something like, what is his velocity on landing, that means we've got to do some other calculations, find out what the final velocity is. It might be a question that's worth having a look at. We can go through that in class to just sort of have another go at that idea of finding the final velocity in that sort of situation.